Next is transceiver architectures. There are different types of architectures already being used in different applications. They have their own advantages and disadvantages. Some of them already known to you, and I will introduce one new, that is called 6-port receiver architecture. So we are going to discuss on the very popular one only. So these are superheterodyne architecture, direct conversion architecture, software radio architecture, and 6-port architecture. So all these 4 different architectures are popular even at millimeter wave frequencies. So here I am showing 2 pictures. The left one is a millimeter wave receiver, right one is a millimeter wave radiometer. So one thing you see, millimeter wave components itself is very small, but when we go for millimeter wave system, it looks big. This is due to the packaging problem. If you look carefully here, all this shiny part, they are actually gold plated brush metal. They are used for packaging. We call it split block technology. So packaging is much bigger, and it's a really problem. People are working on it. How we can minimize the packaging size? Once it's done, then it becomes very small components. So let me start with the superheterodyne architecture. So as you know that here we use some sort of mixer to down convert the signal to lower frequency, and here the intermediate frequency IF is fixed. So for this typical transceiver architecture, whatever I am showing here starts with the antenna and followed by one band pass filter. Then we have a switch channel selector. We can select either the transmitting part or the receiving part by using this switch. So for the receiving part, the first element is low noise amplifier, which should have very small noise figure, that already we know why. And for the transmitter, last component is power amplifier in this chain, and then we have one band pass filter followed by a mixer. So mixer, it multiply the local oscillator signal with the RF incoming RF signal, and in frequency domain it generate if the F incoming frequency if F RF, and the local oscillator frequency if F LO, then F RF plus minus F LO component. Usually we take the smaller one difference, and for this particular example, working at 60 gigahertz, the first mixer, it down convert the 60 gigahertz signal to 5 gigahertz band, and right hand side mixer, then it produces the baseband signal from that 5 gigahertz band. So why 5 gigahertz is chosen? Because 5 gigahertz already we have popular applications, and IEEE 802.11 chipset already available for that 5 gigahertz applications. So we can directly use them. We don't have to design any new chips for this particular thing. So we have to be very careful about the image rejection. So for high side injection, if I consider F LO is greater than F RF, in that case it is F plus twice FIF, and for low side injection it is F minus twice IF. So because otherwise this image frequency will be passed through the filter and it will interfere at right hand side. So we have to avoid them, or you can use image rejecting filter or image rejecting mixer, where mixer itself will cancel the image. Okay, now I will skip this part. Okay, so what are the advantages and disadvantages of superheterodyne receiver principle? So superheterodyne receiver, usually it's very accurate, high performance architecture if you compare with other popular architectures, but it has a problem. Problem is that it uses too many components, particularly filters, and design of band pass filters at millimeter wave frequencies, it occupies very large volume. So component itself, it becomes very big, and not only that, it consumes very high power. So for measurement instruments, superheterodyne principle is very popular, but for handheld devices like mobile phone it is not used. Next is direct conversion architecture, sometimes it is called 0 IF. So, here FLO it has the same frequency as FRF. So, if LO spectrum is given by this, then after multiplication it is directly converted to DC and the immediate IF. So, it has some DC component as well. It in some modulation scheme it is a problem. So, look at the receiver architecture. After LNA we have two mixers for the I and Q channel, in phase channel and the quadrature phase channel, and one single LO is being used. So, for one if we multiply it by cosine, the second one is being multiplied by sinusoidal, and that is how we can recover the I channel and Q channel information. It is followed by low pass filter, then IF amplifier, and then simply we can use a D flip flop as detector, or we can use some other detection technique. So, the LO down convert the signal into two branches I and Q, and then it enables the detector to discriminate the signal at positive and negative frequencies that corresponds to 1 and zeros. It is sometimes called homodyne receiver when the LO is synchronized in phase with the incoming carrier frequency. Since it is not using any BPS and number of components is very small, it is very popular in handheld device applications. Here is one transceiver architecture. We have both transmitter and receiver in homodyne principle. So, you see at the transmitting side the main challenge is to generate that 60 gigahertz signal. So, here one VCO is being used typically in the of the order of 7 to 8 gigahertz range, then it is being multiplied by 8 times to generate that 60 gigahertz signal. And at the input at the incoming side, receiving side, we have LNA, then a variable gain LNA, then the envelope detector followed by LPF. So, after that we have baseband. So, main problem for direct conversion architecture we face with the DC offset, because if I look at the spectrum, you see we have some DC value. So, there are many problems DC offset values because of transistor mismatch in the signal path, LO signal leakage to antenna, and so why you see this LO signal whatever it's coming to antenna it's not perfectly matched. So, some of this incoming power can be reflected back towards source, which will be received by the receiver side, and once it is received it will be mixed with LO again. So, it will self down convert to DC component, this leakage. Similarly, we may have near channel interferer leaking, and that can also self down convert to DC. So, we have a DC offset due to that. So, how we can avoid this system? Actually, we can't avoid this scenario, but we can minimize the DC offset effect by choosing a suitable modulation scheme which has low spectral density at DC frequency. For example, if I use simply amplitude shift keying ASK, it will have high DC spectral component compared to FSK. So, for direct conversion, then FSK would be preferred over ASK. Here are some more example. OFDM also, this is popular, which has lower DC signal energy. Next, third one, software radio architecture. So, if you look at the architecture, it does not have any mixer, and from that calculation, radiometric calculation, we have seen that mixer is the most lossy component in the chain. It simply has one band pass filter LNA followed by one ADC at the receiving side, and at the transmitting side we have a DAC, and they can be directly connected to computer data processing unit. So, the number of millimeter wave components it can be minimized, but at the same time we need very high speed ADC and DAC. It is really challenging, and till now whatever ADC DAC available at high frequency, it is very expensive. So, that is why it did not become popular at millimeter wave frequencies, but it is being expected once that cheaper ADC DAC available, let us say at 60 gigahertz, it would become very popular, since it does not need many millimeter wave components. So, but one solution, a subsampling receiver using a high speed switch can relax the AD conversion rate typically by 4 times the baseband width, but we have to use BPF to avoid image frequencies. So, next is the fourth one, 6-port architecture. It might be new to you. So, originally this 6-port architecture was proposed as a reflectometer to measure reflection coefficient of any device under test. That means simply S11. When we deal with S parameter, you remember that it is a complex function, it has both magnitude and phase, and a 6-port reflectometer, it can accurately measure the complex S11 of any given device, and later it was used as a millimeter wave receiver with some additional modification. Now, it came actually, if you look at the date of inventions or introduction, this millimeter wave 6-port receiver, or as a whole this 6-port receiver, it is the latest technology. It around 1993 to 94 actually it was introduced as a receiver, and it, if you compare the performances, it provides the best accuracy. Typically, if you want to measure phase of incoming signal, it can provide an accuracy of the order of less than 0.01 degree even at millimeter wave frequencies, as claimed by different publications. So, let us see what are the different function of ports. So, we have 6 ports here. One port is used for the incoming RF signal, second port is used for the local oscillator, and another remaining 4 ports, they are connected to detector diodes. So, in detector diodes we need actually millimeter wave diode, which will give you simply DC voltage, and reading this DC voltage, we can determine the magnitude and phase of incoming RF with respect to the local oscillator signal. Now, let me justify why we need these 4 detectors, 4 port for these 4 detector diodes. So, before that, let me first describe what is the working principle of a reflectometer. Then we will use the reflectometer as a receiver with some modification. So, look at the very basic N-port reflectometer in general. We have port from 1 to N. Nth port we are using for device under test. So, main M for measurement of S11. The local oscillator, it is connected to N-1 port. Now, whole 6-port network, it consists of simply passive microwave networks. So, that is its great advantage. In addition, if you look at the previous architecture, the only millimeter wave active component is diode, nothing else. We do not have any mixer. So, this is another example of mixerless receiver technology, and here we do not use any multiplication in time domain. You recall, for superheterodyne we multiply the incoming signal by local oscillator signal, but here we will be using vector addition. We will be simply adding local oscillator signal to the incoming RF signal. So, port 1 to 3 for a or n minus 2, you can say in general, they are connected to the observation points, and all the incoming signal to with respect to this passive network, they are represented by A, and all the outgoing signal from this 6 port from this n port passive network, it is given by Bi in general. Then using the definition of S parameter, we can express B in terms of A. This is Bi equal to summation j equal to 1 to n S I j A j, where I equal to 1 to n. So, you see here S parameters, it is a complex function. Not only that, signal coming out from the input device or falling on the input device, all are complex function. So, we can represent then Ai or Bi by its magnitude and phase form. Now, assume at least 1 to m ports can be described by gamma. So, that means at least we have m number of equations, m number of solutions, from that we can form m number of equations. So, Aj that is equal to gamma j into Bj, where j equal to 1 to m, m is less than n minus 1. Now, two unknowns we have, An and Bn, they are to be solved. You see, we are using it as a reflectometer. So, if we can determine the values of An and Bn, then we can calculate what is the S11 of this device under test, the reflection coefficient of this device. So, An, Bn are to be solved. So, from this it seems that since we have two unknowns, two equations or two observation points should be sufficient, but it is not, since they are complex quantities, they have magnitude and phase. So, we can form n number of n minus 2 equations from this known 1 to m values. So, we are expressing them in terms of n and Bn, these are the unknown quantities. So, B1 to Bn minus 2, that is equal to this matrix multiplied by An Bn. So, we know the values S parameters. If I go back here, so this linear passive network, we can simply measure its S parameter by using a vector network analyzer, right. So, from that then we can calculate what are the coefficients values starting from A1 to An minus 2 and B1 to Bn minus 2. So, obviously, they are a function of these S parameters. So, they are complex quantities, we can represent them in magnitude and phase form. They are function of both S parameters and gamma I. Now, An, Bn, again they are complex quantities, and it is really difficult to measure these complex quantities directly, phase and magnitude. So, what we measure at millimeter wave frequency, it is easier to measure the power level. So, simply then An square. So, if we want to measure power level, in that case we need at least 4 observation points or 4 equations. So, that is why actually it is 6 port, 4 observation points and 1 for local oscillator, another one for the device under test, or the same port we can use as the RF port for incoming signal. So, let us see here, then the average power at port P1, we have 4 observation port P1 to P4, we are calculating average power available at port P1. So, if I go back, you see the power coming out from port P1, it can be represented in terms of B1. So, B1 it represents the signal coming out from port 1. So, if I take time average, then we have a factor of half. So, this is then half B1 square, or from the matrix B1, this is equal to capital A1 multiplied by small a n plus capital B1 multiplied by small b n. So, we can write down then half into A1 a n plus B1 b n whole square, or we can also express them like this: a n n plus B1 b n multiplied by its complex conjugate. Or if we simplify this expression, we can also express half A1 square a n square. So, you see it is now having only the magnitude part. The second term also it is all having only the magnitude part, but the third and fourth term, for them we have both magnitude and phase. So, this is given for port P1. Similarly, we can calculate average power at port P2, P3 and P4. Now, A n B n, we have already this matrix. So, once we have all these quantities, so we can then calculate A n B n from these 4 power values. Now, you see one interesting thing: the magnitude of A n B n star and A n star B n are the same in the equation 4. Then the other information that can be extracted is its phase. So, but we note that A n square multiplied by B n square, that is equal to A n B n star dot A n star B n. So, it seems that if we use this relationship, since already we have calculated A n square and B n square. So, if we use this relationship, it seems that 3 equations should be sufficient. But the thing is that from that other terms, since we use that cosinusoidal term, and because of the nature of that cosinusoidal function, it phase can lead, phase can lag, but we can't find out simply just solving this 3 equation is leading or lagging. So, we need at least another equation to solve that to obtain the sign of the phase. So, that is why it is justified that at least we need 4 observation points, even though we have that relationships. So, here you see it is explicitly written here using that cosinusoidal term, the same equation 4, but this third and fourth terms we are expressing in terms of the cosinusoidal terms. Now, let us say we are going to use this 6-port receiver, 6-port reflectometer as a communication receiver. So, in that case, what we will be doing? So, if I go back, this reflector port or device under test port will be replacing by the RF input port. So, obviously, RF input it may have a different frequency, so than the local oscillator frequency. So, let us say, let us consider a general scenario. We are dealing with 2 frequency components, FA and FB, and they are in that case AI it is represented by AI into e to the power j twice by FAT, and BI equal to BI e to the power j twice by FBT, and FA equal to if FB, in that case the average power is P1, but if FA is not equal to FB, in that case if we use equation 5, it becomes too long. We have to use both contribution due to FA and FB. So, after low pass filtering, you see this is the expression. So, this is practical realization. The basic principle is that we have to form 4 equations. So, in this first example for a 6 port receiver, this is the incoming signal, and you see cos twice pi f naught t, it represents the local oscillator signal. So, it is being added. We can use one simple Wilkinson power divider. One port will be using RF and at another port we will be using LO. Then at the output port we will be having vector addition of these 2 signals. And for the second, it is now being phase shifted by pi by 2, and it is added for the third line. Again it is shifted by pi by 2, it is being added in the second line. So, similarly for the fourth line we have 270-degree phase shift. So, that is how we have basically 4 equations, and from the first and third, okay, so from the from the first and second, where we have 0 phase component and 180-degree phase shift component, we have the I channel, and from 90 and 270 we have the Q channel. So, obviously after this detector we need many signal processing. So, let me show you a practical implementation scheme of a 6 port communication receiver. So, local oscillator, it is fed to one 3 dB power divider, then it will divide power into 2 components simply without any phase difference between them. It is being fed to 2 branch line coupler. So, if you feed one signal to branch line coupler, it will divide it into 2 components for a conventional BLC with a phase difference of 90-degree. RF signal, it is also being fed to another BLC, and all together it is so used that we have that condition. So, this local oscillator is being phase shifted 3 times, then it is being added with the RF, and you can find out the values here. Right hand side it shows the implementation scheme layout. Let us say we want to fabricate it in microstrip line technology. Already we know how to design a Wilkinson power divider and branch line coupler in microstrip line technology. So, if we fabricate it, then the metallic layout, PCB layout, it is shown here. So, this thicker part, it shows the detector mount. So, 4 diodes will be placed 1, 2, 3 and 4. I am showing you one 6 port receiver. It is fabricated here in IIT Kharagpur, but it is not at millimeter wave frequencies, it is at 2.4 gigahertz. So, you can easily identify 3 branch line components 1, 2, 3, and here this is the Wilkinson power divider. So, LO, it is being fed to this quadrature hybrid coupler, and this is the RF port. Just after RF port we have actually one LNA. Next part is the calibration. Calibration, actually it is another, it becomes very complicated because we are dealing with 6 port. When we go for the layout design, obviously whatever ideal scenario we have considered, that BLC is giving exactly 90-degree phase difference, Wilkinson power divider is giving exactly 3 dB power ratio with 0 phase difference, and we also, in addition to we have connecting sections. So, in practical scenario these are not ideal, it will give you some error, some phase shift, magnitude problem. So, we have to calibrate the system. So, the calibration scheme is shown here. This is the very simplified form. So, what we have to do, we have to express this power available from at port P1 to port P4. Here it is shown P3 to P6 actually, and we have to express them in terms of I and Q, and from that we have to calculate this T matrix by measurement. So, we are not going into details here. So, there is also an alternative 5-port junction, but it's not very popular as 6-port when we go for communication receiver applications. Okay, so till now what we learned, some millimeter wave systems, the effect of noise on millimeter wave systems, and also some popular transceiver architectures. So hope you enjoyed the course, and if you have any questions you can send me by email, so I will answer those. Okay, thank you very much.